Okay, begin. Announcements, let's see. Test 1. March 27th. We're going to finish the material for that test today, so and we don't actually have a lot to go through. It should be a short class. I said that last time, but I think it's going to work out this time. So yeah, so that is a week and a half from now, roughly.
Do we get a review session?
No, but there are review problems to go over, and I'll talk a little bit more about the test now as well. Hold on. Probably something I should do anyway. Give me a second. Let me talk about. Like, while we're going over today's topic, I'll also mention about some things about the test, but let me just give you roughly the format. Drafted it. Let's see. So here's roughly what you can expect. Internet is moving slow for some reason. Format. 6 problems. It's the first thing.
Any bonus questions?
2 will be proof intensive. Right, so about 4 out of the 6 problems will be very computational. So I'll ask you things like, find an inverse, compute this matrix expression, find a determinant, solve this using Cramer's rule. Things of that sort will be 4 of the problems, but 2 of them you'll be doing, I'll be testing you on whether you know how to prove things. And as we're going along today, I will also talk a little bit more about the proof section, the kind of proofs that I'll expect you guys to know about. Yeah, so that's basically going to be it. You will have the entire class time. So I have an hour and 50 minutes to do the 6 problems. So basically, I expect you to know how to compute inverses. Of course, find determinants. Expect you to know how to solve systems. Of course, you should know multiple ways on how to do this. So basically, know about when a system does not have a solution, when it does have a solution. If it has infinite solutions, you should be able to figure this out and write it down. If it has a unique solution, you should be able to figure this out and write it down. You should know how to solve it using row reduction as well as solve it using something like Cramer's rule. What else? yeah, those are the main things. I do also expect you to know, find determinants and discuss or apply the determinant theorems. Right, so you should know, for example, like the determinant of a product of matrices is just a product of the determinant. So you should know that if you know a determinant of a matrix and I made you go through and find the inverse and then ask you, what's the determinant of the inverse? You should know it's just 1 divided by the determinant of the other guy. Okay, so things like that. In terms of the proof, in terms of proofs, I'll have one question with a lot of little proofs. I don't know how much it will be, but these are things that you can sort of prove by like a 1-line or a 2-line. If you really understand the concept, it shouldn't be too difficult to come up with. So it might just be me asking you a bunch of true or false and justify your question, or something similar to that, where you can usually knock it out in 1 or 2 lines. And then one question with an involved proof that's going to take you some time to come up with an argument. Right, so there'll be one question where there are a lot of little proofs, kind of like the guys who show up on your quizzes, where you know there's just a 1-line, or a prove or disprove, where you can give an example and things of that sort. So that there'll be one question where I'll have several parts of that. And then I'll have another question where there's like a big thing that I need you to actually give me an argument, go through it, and prove it. And yeah, the proofs in general, it'll also involve things that I will talk about today. But that's sort of the gist of it, really. Yeah?
Can we use scratch paper?
Yes.
Yeah.
But for the test, it's not like a quiz. Partial credit is allowed, so you should explain as much as possible. And I'll be grading you for the steps and just your general sort of understanding of the concepts. So it'll be a fully contained paper where you write down your solutions on the paper. So if you're using scrap paper, use it sparingly. Just know that whatever you do on scrap, you have to copy it into the booklet. You'll have a booklet that you're going to write into. Any other questions about that? Yes?
To study for this test in general, like, would you say like the suggested homework problems and like the homework online homework is enough, or is that like kind of
enough? I also have a small review online.
Okay.
But I would recommend going over the suggested problems, especially for proof type things. I think in terms of computation, you going through the homework is probably enough, or you just looking at what we did in class is enough. But in terms of practice on the proofs, because the homework doesn't test you on proofs, so if you want to practice proving things, you probably want to go through the suggested problems and do the problems that ask you to prove things. As well as, I would probably start with my review that I posted online. Just sort of go through the things there. But if you want extra practice, especially on proofs, go through the suggested problems. So review online. So on my website, I gave you a review. And an additional resource is to do suggested problems, right, which are listed in my syllabus. Suggested problems to prepare for proofs. Another option is to go over the quizzes where I ask you to prove things, kind of cover up the solution, and see if you can reprove the things on the quizzes. Especially if it's been a while and you don't remember the solution I posted, that's also good practice. Yeah?
What kind of proofs do you want us to know? Or just like all of them?
Yeah, how to prove something in general. Like it's not going to be, it can involve, there'll be like on quizzes, right? Especially this short one, you'll have a lot of proofs like kind of like on the quiz, as well as suggested problems. And of course, kind of use common sense here. If there's something in the suggested problems that took you like 5 pages to work out, obviously I'm not going to put that on a quiz. It should be able to something that you can prove in 1 page. right? So not exactly a one-liner, but something that you'll take like a half a page to a whole page to prove from the suggested problems. I'll also might ask you to prove parts of properties or theorems. Some of these guys I'll talk about today. Right? And something like the equivalence theorem might be a good thing to go over. So for example, in the equivalence theorem, I gave you like 5 things that were equivalent, right? I might ask you to do a proof with 2 of them, right? Prove that this thing implies that thing, right? So not only do you have to know, like for the equivalence theorem, when I did the proof, that was long because I was proving like 5 different things. But just kind of imagine I could give you like a chunk of that. Or if there's a property with like 5 properties, do you know how to prove each individual property? I might ask you to prove this property, right? Right, so something like this is like, if you know A and B are invertible, I might ask you, is AB invertible? Right? That's a good short proof. What is the answer? It is invertible. How would you prove it?
And we have a theorem that the product
Okay,
is.
like that's the property.
Okay, but what would you do?
Like when you switch it, they both have inverse.
Yeah, so how do you write that down? Because you need to know how to write it down. Yeah?
By determinant.
Okay.
Determinant of A and multiplied by.
I mean, by the time you get to the first test, there'll be a couple ways you can actually prove it. But yeah, go. Tell me what you're thinking. So I might ask you, this is a good example of a short question, right? So prove or disprove. Right? In which case, those are the kind of questions where I don't tell you what the answer is, what you should be aiming for, but I kind of expect you to be familiar with things enough to have an intuition as to what might be true or what might be false. So yeah, so if A n by n and B n by n are invertible, is the product AB invertible? So your answer would be, so let's say you say yes. Okay, justify that. Yeah.
Just because A and B are like they have an inverse, so the determinant is not 0. So the product of the determinant is not going to be 0.
Right. So you could do a determinant argument, which here you have to actually employ a part of the equivalence theorem. So you first state something like, so you would have to state a statement like something like, we know x is invertible if and only if the determinant of x is not 0. And so then we can show that the determinant of AB is, by the determinant theorem, the determinant of A, determinant of B, which would not be 0 because individually these are not 0. Since determinant of A is not 0 because A is invertible, and determinant of B is not 0. So this means the determinant of AB is not 0, which implies AB is invertible. That's one possible solution. Another possible solution is literally to just tell me what the inverse is. What would that be here? We actually have a theorem about that. Or you could say something like, yes, AB inverse is equal to, right, the shoes and socks on, B inverse, A inverse. Since, and then you show me. How do you prove that that's true? Yeah?
That B inverse A inverse times A B.
You'd have to show that if I multiply them, what
You get
happens?
the identity.
So this guy would give me the identity, so that would become B inverse B. And this guy gives me the identity, so that just equals the identity. And so that would end the proof. Right? Something is an inverse. If you multiply it by the other matrix, you get the identity. Right? So you could go one of two routes. Neither of these are super long or complicated, but they do require you to have knowledge of what it means to be an inverse. So this is using directly the definition of an inverse. This is sort of you going by what we learned from the equivalence theorem, that the determinant has to be non-zero because the reducer echelon form of the matrix has to be the identity, and that means the determinant. Right, so there are a couple ways you could reason through a problem. Neither of them would be super long. So like this could be problem 2, part A, and that would be fine. Right, so that's just an example of one of the shorter proofs that you can kind of do. So you can be prepared in like one problem to do like 4 or 5 of these little guys. Right? And you'll have many routes to the argument, but you need to pick one and show it correctly.
In the exam, are there going to be any bonus questions?
Yeah. So there will be bonus questions as well, and they would be on the following topic. So after this, we're going to talk about vector spaces. We're going to bring it back to talking about the first lecture, and so you might have bonus problems on vector spaces, or any of the future topics that I talk about. So we're going to talk about vector spaces, linear combinations, things of that sort, and using those. As well as I might use the bonus to also test you on concepts that I couldn't fit in the test because it would be too long, but I still kind of want you to know, so I might slip that into a bonus problem instead. So things of that sort. I'll talk a little bit more about the kinds of proofs we can do and how I want you to think about them going through today's lecture, but I first just want to clarify something from last time. Because in a frenzy of everyone sort of telling me what to do, I'm sure I made a mistake on the board somewhere in terms of the inverse of that 3 by 3 we were doing. So just to set the record straight, and this is a great research. I'm using Wolfram Alpha to figure out the answer here, so I don't want to go through that again. That's going to take forever. So we wanted to find the matrix of this guy. And I think one or several of our signs were off by whatever we did. But just for the record, if you want to go over that example and find a mistake, or just redo it on your own, the answer you should get is the following. I'm going to factor out a quarter. And so it's -3, -5, -1. So the first column should have negative numbers in it, and the other ones were positive. I think we had a negative somewhere else. 5, 7. So that's the actual one. I think last time we had some signs somewhere that was off.
Correct.
Okay. So for the rest of today, it's not going to take a long time because I'm going to discuss some properties, long overdue. I think some of them we've been assuming, but I just want to set the record straight as to what we can assume works with matrix algebra and what we can't assume works with matrix algebra. And because I don't really want to write these all down, I just type them up and I give you guys, and we'll just discuss them. So just pass these around. So word of caution, don't just throw this in your notebook and never actually read it. Go through this, make sure you read them. I will expect you to be aware of these properties. And you should be able to use, yeah. You need,
Oh, right here.
oh, there should be more. Just pass it. Right, and you never know. They might be the key to you solving some sort of proof. So in that example where I was talking about knowing that two matrices are invertible, is their product invertible? You sort of pulled on that rule that you knew, or the property that you knew, that if it has an inverse, the determinant is non-zero, and the determinant of a product of things is the product of the determinant, so that has to be non-zero. And you kind of, in order to prove something, you kind of pulled on facts that you know from somewhere else. So the matrix properties, not only do they sort of tell you what you can and cannot do with matrices, but they will give you ideas on facts that you can pull on in order to prove something else. So that's another reason why they're important. And it can give you a lot of intuition as to some things, as you can prove some things. As well as the properties themselves might be something I test you on. So for example, so you see here, for example, in property set 3, the properties of inverses, I told you that AB inverse is B inverse A inverse, right? So I could tell you to prove that that is true, for example. Or I can ask you any of these kind of things. Or can you actually prove this small theorem? If B and C are inverses of A, then B is equal to C. Could you prove that? By the way, here's another thing that I could probably ask you to prove. Let's just see if you guys could reason through it. Let's say I have A times B equals C times B. These guys are matrices. Does that imply that A is equal to C?
Yeah.
What do you guys think?
Yes, I think so.
Yeah? It does not. That would actually be false.
Wouldn't you have to use like B inverse?
So this is an example of what I'm talking about, right? Don't think in terms of real numbers. There is no cancellation law for matrices. This is one of the reasons why you need to see the, yeah.
I mean, right side multiplication by inverse B.
That's what I was thinking.
Yeah, but how do you know B is invertible?
We've been operating in square matrices that are, I mean.
I never told you this is square either.
Okay.
Let me refer you to the bullet points here. Okay, so I mentioned things in the bullet points here, for example. If you look at the second bullet point, if it is not stated that the matrices must be square, do not assume they must be square. Things like that. There are important things that you cannot assume. So if the question were, B inverse exists, is it true that AB equals CB? Then the answer would be yes. If I ask you this question in general and I don't tell you that, the answer is no. Right? So things like that, little attention to detail, that would be important. So one thing I don't want you to walk away thinking is that something like this is true in general. It's not. It has to be the case that you have a bunch of square matrices, and it has to be the case that the B has an inverse. Right? It's possible for everyone to be square, but the inverse doesn't exist, and it still wouldn't work. Right? So for something like this to work, you have to have 1, all the matrices are square, have the same size. 2, B has to be invertible. If I do not tell you that, it is not true. Can you give me a condition in which that would be true? Besides the one I just gave you. So this is a possible condition. You can say that would be true if they're all square and B is invertible. Can you give me another case in which that would be true? Yeah.
B is a
What
zero
if-
matrix is not true, but if
what
A
if-
and C are zero matrices.
Okay. How did you get to that thought? Sir, walk me through how you thought of that.
Well,
Yeah. No, go. Harris.
Yeah.
Yeah.
So,
This is random. Yeah.
if E is equal to B, right? If A is 0 and C is 0, then both A times B is going to be 0 and C times B is going to be 0.
Okay.
And hence, B is going to be, no, B is going to be.
There are more cases than that.
Yeah.
What if B is an identity matrix?
Then it's not true if B is an identity, because you don't know that A is equal to C.
Oh, okay.
but like any case where A is equal to C, it would be true.
Yeah,
So like you could just make up any case.
sure. I'm looking for something
Do
else.
the same size?
Huh?
Do you have to do the same size?
Sure. Give me some other things that you can examine here. Remember, we can do matrix arithmetic. We can add things, subtract things.
So,
Can you think of an idea like that? What if I subtracted, say, CB from both sides? That would give me the zero matrix. Now could you come up with? So that means that A minus C times B, which by the way, the order that you factor the B off matters when it comes to matrices. If you put the B over here, you're wrong. B has to be on the right side. Okay? And that equals the zero matrix. Now what can you say? So Harris got half the answer. B it would have to be the zero matrix, but you can say or A would have to equal C. So that is even a far more general statement. You can make that statement about whether they're square or not, whether they're inverses or not. That would be a statement that's true in general. But as the statement as written, if I don't give you any qualifications, it's not a true statement. So you'd have to either have this condition met or have that condition met that I mentioned before with them being square and then being invertible. So little things like that, they are going to be important because at different times you're making different assumptions depending on the situation you're in. So I have to tell you, you can't really make an assumption unless you're kind of given that. Or the conditions of the problem kind of force that on you. So for example, if I tell you that A is invertible, you can assume, even if I don't tell you, that its determinant is non-zero. Because it has no choice. Right? We have a proof that says if it's invertible, its determinant is non-zero. So things like that you can assume if I don't tell you, but there are other things that you can assume if I don't tell you. And knowing the difference is very important. So those are some examples of things you have to look out for. Right? And don't get away from this intuition. I know that if with real numbers, in the case that the B was not zero, this can basically always work. But matrices are a little bit more nuanced, right? So don't just assume that everything that works with real numbers will work with matrices. It's actually not true. We know that that's not true for multiplication, for example. Matrix multiplication is not commutative, even though real numbers multiplication is. So be careful what you're assuming. And I know a lot of times if I ask a question and students find it sort of difficult to do, they'll just make up an assumption that wasn't given to them and then solve that problem. But it's like that wasn't the problem. Right? So you really need to be careful with that. Has someone had their hand up yet?
But wouldn't that be assuming A minus C is defined?
Hmm?
Like what if A and C aren't the same size matrices? That wasn't given to us.
Okay,
It's the same size.
consider that.
Well, yeah, if A and C are different sizes, then it's never, then AB does not equal CB.
Okay, this equation could not be true if A and C were not the same size. Because B is obviously the same size. And the size of a matrix multiplication is dependent on the size of the two matrices, right? I have to have a certain number of columns and rows here. If this guy didn't have the same number, if the dimension of these two weren't the same, the dimensions of the products would not be the same. So if you're given this equation, it is necessarily true that the size of A and C have to be the same.
is it also why the order of distribution matters?
Well, the order of distribution matters because matrix multiplication is not commutative. And the order, by the way, this, if you look at that, that's actually a property from this, that's from property 5. Right? But there are a lot of things like that that you guys need to know. So like if, for example, in property 5, this is one of the questions where you kind of have to be very pedantic. Well, from now on, if you're doing any math class, you kind of have to be super pedantic, more OCD than you've ever been. So if you're looking at property 5, for example, which says that B plus or minus C, which by the way, for this to be defined, B has to be the same size as C, because when I was defining matrices, addition, I said you can only add matrices of the same size. So by the fact that I wrote this down, you can automatically assume that B has the same size of C. But this is equal to BA plus or minus C, right? Now it's very important that when you look at this property, I want you to notice things like, it's just as important to notice what I'm not saying as opposed to what I am saying, in some sense, right? So notice that I did not say this, right? That would actually be wrong to assume that, right? If it could go the other way, I would give you a property that says it can go the other way, right? If I gave you a property that says things fall in this order, literally know that they will always fall in that order. If it were possible for the order to change, there will be another property that tells you, oh, by the way, we can change the order. Are you guys getting what I'm trying to say? So you have to be very careful because we have all these biases from the math that we've been doing up until this point, and they just don't work here. Right? So you have to be careful about the assumptions you're making. Like if there's a property that says something in one way, don't assume that it can work in some other order, or you can tweak it into, you can't tweak it. If you can, there'll be another property that says you can, right? Don't do anything unless there's some sort of property or some sort of theorem or some sort of logical reason that says you can do that. Yeah.
If you can switch the order, though, it implies that they're square, right?
No. Right, you can come up with matrices that are square that when you multiply them in the other order, they're not the same. Yeah.
Can we use the proof type where we give you like a 3x3 general example and then say with inductive reasoning it would be true for n by n or m by n?
Sure.
That's fine.
Yeah. I don't think, at the moment, a problem like that you can probably expect on a final, but I don't think at the moment I'm going to ask you guys to prove things arbitrarily where you have to do the ellipsis thing. So there are properties that work in general that if it's going to be cumbersome, I will tell you, only prove it for the 2x2 case or only prove it for the 3x3 case. A property where you have to use actually induction, I would ask more for something like, so here's another kind of question that you can sort of expect. So let's look at property 4, for example. Right? So property 4 is a fact. So I can say something like, given that A times B plus C is equal to AB plus AC, not BA plus AC or BA plus da. That's what it's equal to. Prove that something like that I could ask you, right? So that's me like extending a rule. So I can tell you a rule, hey, this rule works for 2 things in the parentheses, but it also works for more than 2 things in the parentheses, which by the way, based on this is not something you can assume, by the way, it's something you'd have to prove. How would you go about proving something like that?
You can add all parts of A1 and A to make a single matrix.
Okay.
And then
Give me a framework to work in here. Huh? Meaning, I do this as a direct proof, proof by contrapositive, proof by contradiction, induction. Give me a framework. Yeah.
Induction.
Induction would be a good framework in which his idea would be applied. Right? So basically, you'd say proceed by induction. I'm just giving you a very concise version here. I'm leaving out some details. Your base case would be that given property. Assume it works for 2 things inside the parentheses. Then I would do my inductive hypothesis. that says it works for n things, we show that it will work for n plus 1 things. So this is equal to a1 plus da da da, n. We show that if I put in an extra guy in there, that the formula will extend to cover that guy. And then what you could do is say, for this guy, just think of it as, for this guy, just think of it as all of these guys I'm calling b plus an plus this, which equals to ab plus an plus 1 by the hypothesis. Well, that's actually by the base case. By the base case, I know that if there are only two things in parentheses, the base case tells me that this is true. And this part here is going to be aa1 plus da 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 all the way up to aan. And that's by the hypothesis. And so it's true in general. And you'd end the thing there. So that's an example. Right, so if there's some rule that you need to extend to a larger number of matrices than you're currently given, induction is usually going to be the way to go. So if I say something only works for 2 or 3 matrices, show that it will work for any number of matrices I pick. Induction is probably how you're going to want to go. Because if we're not talking about the specific entries of a matrix, everything else with a matrix kind of has to do with integers. And positive integers, the number of rows and the number of columns, or the number of matrices you have. These will be non-negative integers. And induction is great at proving things over non-negative integers. So, yeah.
That b is just representing a1.
The b is representing the
okay.
sum of the first two.
Okay.
By the matrix as addition, that's just another bigger matrix, whose components are just the sum of the corresponding components. Yeah.
So that b represents b plus c, right?
This b represents this here.
Which also represents b plus b plus c.
Well, yeah. When I call all of this b, I'm thinking of this guy as representing the c from here,
Oh.
which means I can do this. But the b is actually this, so the b brings me back to here, which I assumed is true by the inductive hypothesis. So that branches out into this, and then I have that. Right, so things like that you can be expected to prove. I can tell you, oh, by the way, here's this property, extend the property, right? And you'll know that, oh, induction is probably what I'm going to do here, and I have to figure out how it tweaks. Or I could say something like, suppose it would be annoying with 3 by 3. It'll probably be too annoying for me to talk about that with 3 by 3. Let's talk about it with 2 by 2s. Is invertible. Prove. And I might just give you to prove a formula that we know in general, but I want you to actually go through the steps for a specific thing. That A inverse is equal to 1 over the determinant of A times the adjoint. So this is true in general for any invertible matrix, but could you actually write down a proof going through all the steps showing that that is true for a 2 by 2? And by the way, to prove that it is not good enough for you to give me an example like this, and then let's apply that formula to this particular 2 by 2, and oh, hey, it worked out. That is not good enough, right? You'd have to assume you have an arbitrary 2 by 2, and show that on that guy it will work.
You could do it that way, though.
You could do it this way. In fact, that's probably how I would do it. I would say set A equals this with me telling you it's invertible automatically means you know AD minus BC is not 0. And then you would actually continue, compute its adjoint, which you do computationally, multiply by 1 over this guy, and show that the result you get is the inverse. So that's an example. So there could be things that we know in general, but I might ask you to go through the details for a specific case. So I can say, okay, we prove that this equation is true for the 2 by 2 case, or for the 3 by 3 case. That is a very valid problem to ask.
That would be the long proof question, though.
Yeah, that would be a long proof question, yeah. So that would sort of be the long proof question. But it's about, yeah. So I might ask you something like, a nice long proof question would also be something like, we had a theorem that said a type 3 row operation does not affect the determinant. Prove that's true for the 3 by 3 case. I could say something like that. Right? And then I would say something like, you are allowed to assume that a matrix with 2 multiple rows, 2 proportional rows, the determinant is 0. Right? So I can give you a helpful fact that you can use. If I don't give you any facts, then any fact you use you have to prove, or just tell me by a theorem in class this is true, and then you move on. Right? But that being said, I did give you some tips on how you want to read these properties and think about them. But yeah, so property set 1 is really about matrix arithmetic. You're talking about adding and distributive laws and what particular laws from the real numbers would work also with matrices. Right, so that's the set of algebraic properties. I gave you about the algebraic properties of the 0 matrix. What are things you can assume with the 0 matrix? Right, and then there are properties of the things you can assume are true for invertible matrices. Things you can assume are true for square matrices. Things you can assume for the transpose. So if I ask you to prove something about a transpose, these would be facts you can use and draw on. And even things like these small theorem 1 and 2, right? You should be able to think, could I prove that? Like if you want to ask me the small theorem, could I actually write down a proof for that? Property set 5 is a proof about, is properties of symmetric matrices, which I didn't define. Let me define what a symmetric matrix is. Symmetric matrices have very nice geometric properties in certain circumstances, which I'll talk about later. But as for now, just know what they are. So definition. So this is an important definition to know, because if I ask you to prove me something about symmetric matrices, you'd have to know what those guys are. So we call A symmetric matrix. If anyone knows what symmetric matrix is? Yep. If it's equal to its transpose. So examples, I give you one example that covers an infinite number of cases. All diagonal matrices are symmetric. Every diagonal matrix is equal to its transpose. I can give you another example, something like 1, 2. The idea is you want, for symmetric matrices, the main diagonal works as sort of a mirror. So if I put a 3 here, a 3 has to be here. So notice that if I take the transpose of this guy, I get itself. Right? So that's an example. Pretty much anything that, so something like 1, 0, 7. So if I put 3, 4, 1, right? Pretty much anything that reflects directly over this. So this would be 3, 4, because the 3 matches with the 3, the 4 matches with the 4, and the 1 would have to be here to match with the 1. That's a symmetric matrix. So for example, So for example, and here's how you can use this to your advantage. If I ask you to say, let's say I ask you to prove something about two by two symmetric matrices. And you want to pick an arbitrary such matrix, what would you pick? Right? Some general theorem about 2 by 2 symmetric matrices. And you're thinking of A as such a matrix. What would you write it down? Yeah?
A, B, B, C.
You can automatically assume that the matrix will have this form. That this and this will be the same. And more than likely, if you let those not be the same, you're going to end up having to do way more work than you would have otherwise. Right, so I can tell you about a property of a matrix, and that would determine the kind of generic form that you take. And then you can continue with whatever you want to prove. There's another thing. There's something called anti-symmetry. So A, definition, A is called anti-symmetric if, do we know that one?
Like skewed symmetric?
No, skewed symmetry. Well, it's the same, yeah. What is it? Just for a negative sign. The word anti comes from the fact that if you multiply by a negative, it flips the orientation of the matrix. Okay. Let's end with something here. And for now, you're allowed to, of course, use this sheet that I just gave you. Let me see if we know how to kind of use this sheet. Let's say I ask you to prove the following. Prove that if A is symmetric and invertible, then A inverse is symmetric. Give me an argument for that.
If A is symmetric,
Yeah?
Direct proof.
Okay, direct proof.
Just put in, without loss of generality, you can use it 2 by 2 probably. And do A, B, B, C. And then figure out what the inverse of A, B, B, C would be.
That's kind of problematic because the formula for the inverse of a 2 by 2 is way simpler than the formula for the inverse of general things. So how do you know that something doesn't get screwy?
Then could you do it with a 3 by 3 or would that take too long?
I probably wouldn't want to. But
we know that A inverse is going to be the, it's going to be the 1 over the determinant.
By the way, you need to realize that if you did take that approach, you would have to come up with a reason that it generalizes to arbitrary matrices. So you can say, okay, here's true for a 2 by 2. It generalizes to larger because of this reason. Which means you'll probably, if you did it that way, you'll probably have to end up doing like an induction proof, for example, to show me that, okay, I proved for 2 by 2, I'm going to use this fact to prove that it can work for any size. We'd have to justify that.
So like we know the A inverse is the adjoint multiplied by 1 over the determinant.
Okay.
So assuming that A is symmetric and invertible,
Yeah?
All we would have to show is that the adjoint is symmetric,
Sure.
and then because the determinant exists, so the inverse would exist then. It's just a constant. The determinant would be considered a constant, and that's fine with property.
So you'd end up having to prove that the adjoint is symmetric. How would you
Yeah.
prove that?
by induction.
3 by 3 gives,
Huh?
or 3 by 3.
Yep, then you have to show that, oh, by the way, if it works for 3 by 3, it will work for larger.
Wouldn't that mean that the cofactor matrix, you just need to prove that the cofactor matrix is symmetric, since the transpose.
Yeah, that's what he said. But how would you know? How do you know the cofactor matrix is symmetric? Yeah?
You could do it by direct proof, just algebra, using the theorems here. So if you write down A inverse.
So tell me some facts that you're pulling on now.
Well, then A equals A transpose, we know that.
Yes, we know that A equals A transpose. Yes?
We can see that the transposition of matrix multiplication flips the order, it takes the transpose of both. So we have that parentheses.
So what factor are you using?
we
That
have
this
parentheses A, yes.
is this?
Yes.
That's the factor you're using? Okay, and what's your argument on that?
Well, so if we write, we know that A is invertible, so we can write A inverse A equals the identity.
Sure.
And then we can write in parentheses, so if we try to take the transpose of A inverse A, sorry, A inverse A.
Okay.
I mean, it doesn't matter, I know, but I wrote it down this way.
Yeah, then?
So that's equal to A transpose, A inverse transpose. Right. So then the left side results in the identity.
Sure.
And so then if we were then to multiply the extrema of that on the left side by A inverse.
Okay. So you want to multiply that equation that we have by A inverse on both
left
sides.
side.
So you could then say A inverse times the identity, but that's just going to be A inverse, is equal to A transpose, A inverse transpose.
And then, yeah, but you have on the left side, you didn't multiply the right side of the equation by A inverse.
Okay. Yeah.
And we've
And
already
then?
seen that A inverse A, sorry, A inverse A transpose, since A is symmetric, that is also equal to the identity.
Yeah, you sub out that.
Oh, so you have to use the fact that A transpose is A.
Yes,
And so that would be the identity.
right.
And so you get that A inverse is A inverse transpose.
Yes.
Yeah, that's one way you could go about it.
No question.
Right? So you're using properties. There were easier properties to use.
The determinant of A equals. the
So,
determinant-
like, one thing we also want to talk about is the approach. You see a problem like this, what is the first thing you kind of think about? Let's start there. You read this, what is the first thought that comes to mind? Yeah?
A is equal to the transpose of
Is it symmetric?
Yeah?
A. And can you use the number 5?
But I want to go a little bit higher level than that. That should be the first thing you think about, but why was that the first thing you thought about?
Because it says symmetric.
Because it says the word symmetric. So here's the goal. You see a problem that you want to prove. The very first thing before you do anything, you need to make sure you understand the question. This involves meaning you know the definition of every word in that question. So when I read this, my first thought is going to be, what does symmetric mean again? Need to know the definition of symmetric. So I need to know this. Okay. And the second thought you should know is really know what you want to prove. Now, once you realize that this is the definition of symmetric, you should then know immediately what the end goal is. How would I prove that A inverse is symmetric? I need to show that A inverse fits this definition, which means I know I need to start here and end here. Right? So this already gives you a map. Right? You just look at the question, but you already have a map. You know where you need to start, where you need to end. That all starts by first you knowing the definition of what symmetric means. So knowing your definitions is important. So there's a study tip. Know your definitions. Know them very well. Because when I give you a problem, the first thing you're going to make sure you know how to do I know the definitions of every single word in this problem? That is going to translate into a bunch of equations or properties that you know. That is going to give you the starting point. The very next thought you have should be, what should my end goal be? You're asking me for something. What would proving that involve? What would I have to be able to say in order to say that A inverse is symmetric? I would have to be able to say A inverse fits the definition of symmetric, meaning if I replace A with A inverse in the definition, that equation has to be true. Okay? So the thought process is just as important here. You're like, you can see someone do a solution and you're like, yeah, I can see how it went from one step to another step. Yeah, I can understand that. But would you have known to do what he did in the first place? How you need to know, that's the tricky part. And that means, 1, you need to know definitions. 2, you need to translate that definition into a concrete mathematical statement to use as your starting point. 3, you need to know the definition of the end goal and translate that end goal into a mathematical statement. 4, figure out the best way to go from here to there. Now, based on the problem, that might be, okay, it would be good for me to use induction, or it would be good for me to do a direct proof, or it would be good for me to use a proof by contrapositive. But that is that's the general approach that you want to take. You know, so if you want to think of a strategy of how to approach proofs, that's kind of a general overarching high-level language strategy, and the details are kind of something you have to work out. But at the very least, you should be kind of knowing what do I have and what do I need to prove, right? And that starts by you knowing the definition. So, yeah, you stated this fact first because you realized, oh, symmetric is in the word. What does that mean? It means this. What do I need to prove? That A inverse is symmetric. What does that mean? It means this. So I need to use this to prove that, right? You need to start there, right? Now, if you don't even, if you had no idea what symmetric means, forget it. You're not going to be able to do this problem, right? You're just going to start making up random facts. Assume A is square. Oh, let's look at the adjoint. Let's look at this. Let's look at that. Let's use these other complicated things. You're gonna be right? You really want to minimize that you're doing on an exam, and that's sort of a general approach. Okay, so when I give you the definitions, they are important. When I give you properties, they are important. There is a property, by the way, which I said you were allowed to use this property on here. There is a property that relates transposition to the inverse. If you look in property set 4, problem part 5.
Do you have to prove that or on the exam?
Is that given?
Well, it's given here, so no. So we know if I look in property set 4, part 5, I have this property, that if I take the A transpose and take the inverse, is the same as A inverse transpose. So say you remember that property, your work would actually be a little bit easier for you, right? How could you get from this to that using that statement? Yeah?
A transpose is A.
Directly, because you know what symmetric means. So you can say, and then you get your like right away, one step. You see the difference between. So this is also an illustration that you can make a problem very hard, very easy. Now, if this is what you saw first, that's fine, as long as you can do it quickly enough before time runs out. But if you remember this property, then you can know that A is symmetric means A equals A transpose. From class, now if you don't remember the particular property, you don't have to say, oh, property 4 from the handout, part 5. Like, sure, okay. It's okay to say, from class, we know this fact. This implies that A inverse is equal to A inverse transpose. Since A equals A transpose, done. Right? And there were multiple approaches to solving this problem. By the way, a problem like this would be in the short proofs. Like, I'd be able to expect you to knock out a problem like this in relatively a few steps, right? You could have gone the adjoint method and examined the adjoint, but that would be more complicated than either steps here. But the upshot is that when you're proving something, you really want to set a roadmap for yourself so you don't get lost and start pulling on random facts all over the place. To make sure you're not doing that, you need to start with knowing the definition. So you kind of have mathematical statements to describe the words that I'm giving you. Know the definition of the goal that you want to end up with. You want to show that if A is symmetric, then this is symmetric. So you need to start here and end there. And then it's just a matter of how do I get from here to there? And you can use facts or properties from class. Sometimes you might have to write something out, do an induction. Sometimes you might have to do other things. But yeah.
So you want us to state like A times A inverse equals identity? Like you want us to state it out? We can't just write. We can't just like replace it with identity.
Where?
Like how you wrote it in on those bullet points. Like you wrote them out. Like those are properties that we know. Like do we have to state that, or can we just directly write identity?
Well, I would mention this, but these I mean, it's okay if you don't specifically state this, but like by doing this, I would know that you know that. But I would be safe if you're not sure if you can get away without stating something, just state it. Yeah.
During the test, we ask just to do the proof, like by induction, direct.
I'm not going to tell you what technique to use. I'm just going to give you a statement, prove it, or disprove it. Because really, to be completely honest, not that I'm never dishonest in this class, this is why we need human beings. The computational part of linear algebra is not the important part. That's the part that computers do. We don't need people for that part. The reasoning of connecting ideas together is why you are here. It's the main thing why you are here. Now I understand that some of you have not seen proofs before, and that's why I've made the majority of the first exam mostly computations, but it's not the point. Right? The computers can do the computations. But you need to be able to tell the computer what computations to do and when, and that requires you to understand a conceptual knowledge of everything. So we can stop there. So read over these properties, don't just ignore them, make sure you know them, and you can use them as facts. And of course in the test, if there's ever a thing that you're not sure about, let's say you want to use a fact and you're not sure if you can assume it or not, you can ask them. You can say, I want to use this fact. Is that okay if I don't prove it? And I'll tell you, yeah, that's okay. So, and there,
We can assume facts.
Huh?
We can assume facts, but if
In general, if I gave you a theorem in class, you can assume it. Okay, so stop there.